Beneath the Cascade Range, the picture is no longer one of isolated volcanic plumbing systems that empty out after an eruption and then fade into geological silence. It is a much larger and more persistent picture, one built on a study published in Nature Geoscience on January 23, 2025, titled Long-Lived Partial Melt Beneath Cascade Range Volcanoes. The research used seismic imaging to peer beneath 6 volcanoes across the arc and found low seismic velocity bodies consistent with partial melt between about 5 and 15 kilometers, or roughly 3 to 9 miles, below the surface. The volcanoes identified in the findings were Mount Rainier, Mount St. Helens, Mount Hood, Newberry Volcano, Lassen Peak, and Crater Lake, also known as Mount Mazama. That result matters because it cuts directly against the older assumption that large magma bodies should disappear once a volcano goes quiet. The Cornell summary of the work says the researchers examined 6 cascade volcanoes of different sizes and dormancy levels, and found persistent large magma bodies beneath all of them, including dormant ones. The study's abstract goes further, saying these reservoirs vary in depth, size and complexity, but remain widespread regardless of how much each volcano has erupted or how long it has been since the last eruption. In other words, a volcano can look calm at the surface and still sit above a substantial long-lived partial melt zone in the crust. The Cascade Range is a particularly important place to test that idea because it is one of North America's most active volcanic arcs and includes a large share of the United States volcanoes classified by the United States Geological Survey as very high threat. Cornell's report notes that the team used seismic waves to image the subsurface around 6 volcanoes in this region. The paper itself describes a systematic model of the 3-dimensional scattered wave field of teleseismic body waves, a technique that allowed the researchers to identify the low-velocity zones associated with partial melt below the volcanic centers. The list of volcanoes in the study tells its own story. Mount Rainier, Mount St. Helens and Mount Hood are among the most familiar cascade names in the Pacific Northwest. Newberry Volcano in Oregon has long been known for a broad volcanic system rather than a single steep peak. Lassen Peak in California has a well-documented eruptive history, while Crater Lake, the remnant of Mount Mazama, is a reminder that a volcano can collapse, refill with water, and still retain magma at depth. The study found magma reservoirs beneath all 6, showing that persistent crustal melt is not limited to obviously restless or recently erupting volcanoes. One of the most significant details is depth. The abstract places the melt bodies between 5 and 15 kilometers, or about 3 to 9 miles beneath the surface. That is shallow enough to matter for monitoring, but deep enough to remain hidden from ordinary surface observation. The study says these upper crustal bodies are widespread and do not simply disappear because a volcano has not erupted recently. Cornell's summary notes that some of the volcanoes, including Crater Lake in Oregon, have not been active in millennia, yet still show evidence of substantial magma below. That distinction between dormant at the surface and still active at depth is central to the new findings. The old model treated a large magma chamber as a sign that an eruption might be approaching, while a depleted chamber suggested dormancy. The study points in a different direction. It says large volumes of melt can persist through eruption cycles beneath big volcanoes, and Cornell's account describes the researchers' view that this is not an unusual exception, but a baseline condition for many Cascade volcanoes. The implication is that magma storage may be a long-term feature of these systems, not a temporary pre-eruption phase. The method used to reveal the reservoirs is just as important as the result. The researchers relied on seismic waves and receiver function analysis, using scattered wave fields from distant earthquakes to build images of what lies below each volcano. Cornell says the team needed only very small seismometer networks around each volcano, helped by recent improvements in broadband seismic coverage near the Cascade Arc. That matters because it means this kind of imaging may be more portable than older approaches that required much denser instrument arrays. The findings also help explain why volcanic systems in the Cascades can remain geologically active even when they seem quiet for long periods. The magma reservoirs in the study vary in size and structure, but the broader pattern is the same. Melt can linger in the upper crust, rather than being fully expelled during eruption. The paper says that instead of draining a magma chamber completely, eruptions may release part of the excess volume and pressure while leaving behind enough melt for the chamber to persist and slowly refill over time. That makes dormancy less like a shutdown and more like a slower phase in a continuing magmatic cycle. This is especially relevant for the Cascade volcanoes because several of them have extensive monitoring histories while others have been studied less intensively. The Cornell report says a better general understanding of where magma sits could improve the targeting and optimization of monitoring systems. In practical terms, that means a volcano does not need to be erupting or even showing obvious unrest to justify close attention if a substantial melt body remains beneath it. The study's results support the idea that the hidden plumbing beneath these peaks is more persistent than older models allowed. There's also a broader geologic point embedded in the study. The Cascade Arc is shaped by subduction as the Juan de Fuca plate sinks beneath the North American plate. That tectonic setup generates magma at depth, but the path from mantle production to surface eruption is controlled by the crust above. The study shows that crustal storage is not a minor side effect of volcanism in the Cascades, it is a fundamental part of the system. The reservoirs differ beneath each volcano, yet the underlying pattern repeats across the arc. Mount Rainier, Mount St. Helens, Mount Hood, Newberry Volcano, Lassen Peak and Crater Lake each add a different piece to the picture. Some are frequently discussed because of hazard potential, some because of past eruptions, and some because they have been quiet for long stretches. But the study places them in the same category at depth, volcanoes with enduring magma storage in the upper crust. That shared pattern is what gives the findings their weight. The magma bodies are not isolated curiosities. They appear across a range of volcanic settings in the Cascade Arc, including long dormant ones. Just as important, the study does not claim that these reservoirs mean an eruption is imminent. It says the opposite is more consistent with the evidence. The mere presence of substantial magma does not automatically signal near-term activity. Instead, the reservoirs can remain in place for long periods, with their melt fraction, structure and pressure state evolving slowly through time. That makes the Cascade findings less about immediate eruption and more about the hidden durability of volcanic systems that may have seemed from the surface to be settling into dormancy. The broader geological setting of the Cascade Range provides the framework that allows such long-lived magma systems to exist in the first place. This mountain chain is not simply a line of isolated peaks, but the surface expression of a continuous subduction-driven process that has been active for millions of years. At its core is the interaction between the Juan de Fuca plate and the North American plate, where the denser oceanic plate descends beneath the continent. As the slab sinks, it carries water, rich minerals into the mantle, lowering the melting point of surrounding rock and generating magma at depth. That magma does not move directly upward in a straight path. Instead, it accumulates, stalls, evolves and redistributes within the crust, creating a layered system of storage that extends far beyond a single volcanic conduit. This process explains why the Cascades are characterized by stratovolcanoes, composite structures built through repeated eruptions of lava, ash and other material over tens of thousands of years. Yet the surface forms only hint at what lies below. The crust beneath the range acts as both a pathway and a reservoir, where magma can pause for extended periods. The recent study showing persistent partial melt zones beneath volcanoes such as Mount Rainier, Mount St. Helens, Mount Hood, Newberry Volcano, Lassen Peak and Crater Lake highlights how uniform this deep-seated behavior can be, despite very different eruption histories at the surface. A key geological concept behind these findings is the idea of transcrustal magma systems. Rather than a single large chamber, magma is distributed across multiple deep levels, forming a vertically extensive system that can span from the mantle crust boundary up to shallow depths of around 5 to 15 kilometers, or roughly 3 to 9 miles. Within this system, magma does not exist as a continuous liquid body, but as a mixture of melt and solid material. These regions can remain in a partially molten state for extremely long timescales because the heat supplied from below is balanced by gradual cooling into the surrounding crust. This balance allows magma to persist without necessarily triggering eruption. Dormant volcanoes within the Cascades illustrate this principle with particular clarity. A dormant volcano is typically defined as one that has not erupted in historical time, but is still capable of future activity. In the Cascades, dormancy does not imply that the system has shut down. Instead, it often reflects a state where magma supply continues at depth, but conditions at shallower levels are not favourable for eruption. The presence of partially molten reservoirs beneath long, quiet systems, such as Crater Lake, demonstrates that volcanic inactivity at the surface can coexist with ongoing magmatic processes below. Crater Lake, formed after the catastrophic collapse of Mount Mazama approximately 7,700 years ago, provides a clear example. The eruption emptied a large part of the former magma system, causing the upper structure to collapse and form a caldera that later filled with water. Despite this dramatic event and the absence of recent eruptions, the new imaging indicates that magma remains stored beneath the area. This suggests that even large eruptions do not necessarily eliminate the deep magma system. Instead, they may only partially reorganize it. Further north, Mount Rainier presents a different configuration. It is heavily glaciated and has not produced a major eruption in recorded history. Yet it is considered one of the highest-risk volcanoes in the United States. The underlying geology explains why. Rainier sits above a long-lived magmatic system fed by continuous subduction processes. The detection of partial melt beneath it reinforces the idea that the volcano retains a viable magma supply even in the absence of frequent eruptions. The hazard in such cases is not constant eruption, but the potential for sudden change if pressure, temperature or structural conditions shift within the system. Mount St. Helens, in contrast, has a well-documented recent eruption history, including the major event in 1980. Its inclusion in the study provides a useful comparison between active and less active systems. The presence of magma beneath both St. Helens and more dormant volcanoes shows that eruption frequency is not the sole indicator of magma availability. Instead, it is the state of the reservoir, its melt fraction, pressure, and connection to surface conduits that determines whether an eruption will occur. The southern Cascades add further variation. Lassen Peak last erupted in the early 20th century, while Newberry Volcano represents a broad volcanic field rather than a single central peak. Both still show evidence of subsurface magma. This diversity underscores an important geological point. Volcanic form is not a reliable indicator of what lies beneath. A symmetrical cone, a broad volcanic plateau, or a flooded caldera can all overlie similar types of magma storage zones. Another factor shaping these systems is the composition of the magma itself. Magma in the Cascades tends to evolve chemically as it moves through the crust, becoming richer in silica and more viscous. This evolution is tied directly to the long-term storage within crustal reservoirs. As magma cools slowly, crystals form and settle, while the remaining melt becomes more chemically differentiated. This process can repeat multiple times as magma rises, stalls, and mixes with new inputs from below. The result is a wide range of magma compositions that can influence eruption style, from relatively fluid lava flows to highly explosive eruptions. The long-term persistence of magma also affects the mechanical properties of the crust. Regions containing partial melt are generally weaker than solid rock, making them more susceptible to deformation. Over time, this can influence the structure of the volcanic arc, guiding where future magma pathways develop. It also affects how stress is distributed within the crust, potentially linking activity across different parts of the range. While each volcano operates as a distinct system at the surface level, the deep environment may be more interconnected than previously assumed. Heat flow is another critical element. The continuous introduction of magma from the mantle provides a sustained source of thermal energy. Even if only a portion of that magma reaches the surface reservoirs, the heat it delivers can maintain partial melt conditions over long periods. This explains why magma bodies identified in the study can persist for thousands or even tens of thousands of years. The system is not simply cooling after each eruption, it is being reheated and replenished from below. The distinction between active, dormant, and extinct volcanoes becomes more nuanced in this context. An extinct volcano is generally considered one that will not erupt again, often because its magma supply has been cut off. In the Cascades, however, clear examples of true extinction are relatively rare compared to dormancy. The ongoing subduction process ensures that magma generation continues, even if individual volcanoes remain quiet for extended periods. The presence of deep magma reservoirs beneath multiple dormant systems supports the idea that many Cascade volcanoes exist in a long-term cycle rather than moving toward permanent inactivity. Geophysical imaging continues to refine this understanding. Techniques that measure seismic velocity, electrical conductivity, and ground deformation are increasingly capable of detecting subtle variations in the crust. The study's identification of widespread low-velocity zones beneath multiple volcanoes is likely only a partial view of a more extensive system. As instrumentation improves and data sets grow, additional details are expected to emerge, potentially revealing connections between reservoirs or identifying previously unrecognized magma storage regions. The Cascades also offer an important comparison with other volcanic arcs worldwide. Subduction zones in regions such as Japan, the Andes, and parts of the Mediterranean exhibit similar processes, suggesting that long-lived, extensive magma storage may be a common feature of arc volcanism. The findings from the Cascades therefore extend beyond regional geology, contributing to a broader framework for understanding how magma is stored and mobilized beneath continents. Time remains a defining variable in all of these processes. The formation, evolution, and preservation of magma reservoirs occur over geological timescales that far exceed human observation. A volcano that appears inactive over centuries may still be actively accumulating magma at depth. The study's identification of persistent melt beneath both active and dormant Cascade volcanoes emphasizes that volcanic systems operate on timelines that are not immediately visible at the surface. What emerges from this deeper examination is a more continuous and less segmented view of volcanic behavior. The Cascade Range is not a chain of peaks that switch on and off independently, but a long-term magmatic system shaped by constant tectonic forcing, gradual material movement, and sustained heat transfer. Dormancy, in this setting, represents a phase within that system rather than its end.